All right, I wanted to show an example of some linear dependencies. So let's think about a set of vectors first, and then I'll get into what it means linear dependence. So here's a bunch of vectors. Here's a vector 1, 2, 3. Here's a vector -2, -4, -6. Write down a bunch of vectors. 2, 0, 1, 3, 2, 4, 0, 0, 0, and 1, -2, -2. Now, notice this, well, let me give these names. So this is vector v1, v2, v3, v4, v5, and v6. These are actually the columns of the matrix A that we had in an earlier example, the example about parametric vector form solutions. So we can think of the columns, these vectors forming the columns of this matrix A. And I'm actually doing this on purpose. It's going to turn out to be relevant to some earlier discussion. But let's notice something. So these vectors are related to each other. So a lot of them are, not all of them. Like for example, v1 and v3, you can sort of check aren't really related directly in any way. But so notice, notice some relationships. Among the vectors. So first, maybe one that jumps out immediately is that v2 is -2v1. That's a relationship. In fact, I sort of, in the video where I use this example, this matrix A, I actually said some of these relationships. Here's another thing to notice. If you add v1 and v3, you get v4. So v4 is v1 plus v3. V5 is the 0 vector. And v6 is actually v3 minus v1, I think. If I take this one and subtract this one, I get 2 minus 1, 0 minus 2, 1 minus 3, yeah. So v6 is actually v3 minus v1. All of these things are called linear dependencies. These are called linear dependencies among the vectors. The idea is that you're writing one vector as a linear combination of some of the others. You're writing one vector as a linear combination of some of the others. Even this one, which you might think is kind of weird, we could think of as something like, you know, v5 is like 0 v1 or something plus 0 v2 or something like that, right? I mean, it's kind of silly, but it is still a linear combination in that sense. And so the 0 vector is sort of special here, but it is treated as a linear dependence. And the set of vectors, if we call this set S at the top, I'll call it S. It's not the same S from the previous video, but the set S is called a linearly dependent set because of this, called linearly dependent. Okay, that's the terminology for that. And so that's, you know, that's the example. The thing that I wanted to connect it back to, which is sort of interesting, is if we actually look at there's a way to rewrite these because it's a little bit strange, but, or actually, let me say this a different way. If we look back at A, sorry, and the solutions that we had, especially the homogeneous solutions. So let's just like recall the following were homogeneous solutions these were solutions to AX equals 0 for this particular A. So one of the solutions was, we called it H2, I think. And that was the vector, just look at my notes here, 2, 1, 0, 0, 0, 0. H4 was the vector -1, 0, -1, 1. H5 was the vector 0, 0, 0, 0, 1, 0, and H6. He's actually sort of generated all the solutions, all the homogeneous solutions, 1, 0, -1, 0, 0, 1. I claim these are connected. You might look at these vectors, you might look at these, and then look back at these equations. There's a nice connection among them. You might pause and see, like specifically, can you see how this might be related to this? There's a -1 in the first position, a -1 in the third position, a 1 in the fourth position. What is going on there? Well, okay, let's think about it. So these are solutions to x equals 0. So for example, AH2 equals 0, but that's the same thing as saying the vector whose the matrix whose columns are V1 through V6. If we multiply that times this vector, that's a 0, we get the 0 vector in, I guess, in 3 dimensions. But remember, there's a way to think about multiplying a matrix times a vector as thinking about these entries as weights on the vectors. So we can rewrite this as 2v1 plus v2 plus 0 v3 and so on equals 0. Or really, 2v1 plus v2 equals 0. Or v2 is minus 2v1. So in fact, we've recovered the linear dependence. The linear dependence is encoded in H1 somehow, and in H2, sorry. Dependence is encoded in H2. That's exciting. What if we do the same thing? Let's do the same thing for like the H6 vector. You tried for H4, but let's try AH6, right? AH6 is 0. Again, that means, let me just write this out again, V1, V2, V3, V4, V5, V6, times H6, which was this vector right here, 1, 0, minus 1, 0, 0, 1, equals the 0 vector. And again, if we write this, we rewrite this, this is 1 times V1 plus 0 times V2 plus minus 1 times V3 plus 0 times V4 plus 0 times V5 plus 1 times V6 equals 0. Or V1 minus V3 plus V6 equals 0. Or V6 we move everything to the other side, is v3 minus v1. So that actually gave us that linear dependence. You should check that, you should pause and do the same thing for H4 and check that that gives this linear dependence. And then I just want to say one thing about H5, which is that somehow it gives that linear dependence, which is kind of silly, but I guess maybe the one thing you would say for H5, let's just write H5 down. Well, there's only a one. Maybe I'm going to be lazy here and write it like this: 0, 0, 0, 0, 1, 0 equals 0. So that implies 1 times v5 equals 0. And so that actually gives the v5 equals 0. So that is the linear dependence. It's just sort of given that way. And so somehow the homogeneous solutions are encoding these nice linear dependencies. That's what's going on here. And it does make some sense if you think about rewriting all the linear dependencies this way. And this actually maybe starts to inspire the formal definition of linear dependence, which is, it's kind of nice just for some sort of symmetry to move everything to the same side. So a better way to write the linear dependencies, and I'll get into the more formal definition in the next video, but let me just finish by writing this, is to rewrite, so the linear dependencies were all up here, right? And I'm just going to rewrite them all kind of by moving everything to one side of the equation. So, and having the 0 vector on the other side. So we could write 2v1 plus v2 equals 0. For v4, sorry, I have to scroll a little bit back up. We could write minus v1 minus v3 plus v4 equals 0. Or we could write v1 plus v3 minus v4 equals 0. It doesn't really matter. We can write 1v5 equals 0. And we can write v1 minus v3 plus v6 equals 0. And just kind of, there's a symmetry to putting them all on one side. And I'll get into this more in the next video as to why, even more why we like this when I define linear dependence and independence a little more formally. Okay, I'll just stop there now that I've piqued your interest.